Right, so by the sound of it, you've got through A, B, C, D, and it's parts E and F that you're not very happy with. So I'm guessing that you've been on the calculator and you've put the information into a spreadsheet, and you've got the first column there, the tons, and the price for the Y variable, and I'm hoping that you've got a linear regression worked out. Y equals mx plus b, and you've got the m and the b there, and you've got the correlation coefficient. So I think that answers the first part of the question. So we've got, yeah, you've got the equation of the regression line, and you've got the correlation coefficient, and you've drawn a scatter diagram, but in your on your paper, and that should look a bit like this. I think it's here. So you've got the scatter diagram like this, with your scales. This is on your paper, and you've labelled this as tons, and this is price. And you can see that you don't have to add the linear regression line, but I've done it on the calculator, and you can see that when you try and fit a linear regression line to this data, it doesn't quite work because the data looks more exponential than linear. So we'll keep that in mind, because that's going to be the reason why we're going to do parts E and F. But you can see that that the predictions here, as we get up to 3,000, 3,500, are going to be too low, because it looks like this is flattening off, like the price is flattening off. It doesn't keep on dropping, which is what the linear model is predicting. So the linear regression isn't particularly good for this data. So when you've got data that is either logarithmic or exponential, it's curved rather than straight, then the historical way that used to solve that would be to change the y, to do something to the y variable, and either use an exponential function involving the y variable, or a logarithmic function using the y variable. And for our syllabus, it tells you that it says that it has to give you the change. So what it says here is suggests an exponential model may be more appropriate than a linear. So we consider the variable z equals ln y. You'll have to be given this thing, z equals some stuff. So on my calculator, I go back to my spreadsheet, and now I've got this third column, and I've done equals ln of b1 equals ln of y, effectively. So I've done ln of the price equals ln of b1. Down here I've times it by 1.0, and that forces it to be a decimal, because otherwise it just says ln 3, and it's not very nice. So this is my z column. Okay, so I've got my x column is my tons, price is y, and this is the ln of the price. This is my z column, and it says to find a regression between x and z. So across here I've just done exactly the same as I did between x and y, and I've done it between x and z. So this is a linear regression line linking x, the number of tons, to z, which is the ln of the price. And you can see that the r is not much, actually, because it's not a very good question, to be honest. Normally the r is slightly better, like it's closer to -1 than this one here. So it is a slightly better fit to the data. Normally the change between these two is a bit more dramatic, but I think they've kept the function quite simple. So the x and the z fit together a bit better. So what have we done? We've determined the equation of the regression line of z on x, and we've found the correlation coefficient. So that's E, all done and dusted. And you can be quite mechanical about that. It will give you this. Do a third column. Do these things with the x and the z. Right, the last stage then. Estimate the price per kilogram of strawberries for a production of 3,000 tons. So the x is 3,000, and you're trying to find out what price you're going to get. And it's saying using the three models obtained in B, D, and E. So you've got B is your initial regression model. Now when you did that on the calculator, it would have saved it as F1. Your first thing is F1. So if I go to a calculator page, if I put 3000 into F1, which is the linear equation, the linear regression line between x and y, then for 3000 it tells me the y should be 1.58. So that's the price of tons per euro or euro per tons for my first regression model. Then you would do the same with the line of Meyer. Now hopefully you've got an equation for the line of Meyer, so you put the x value into the line of Meyer and see what price that gives you. And finally you put it into the second regression, the one that connects x and z together. So you put 3000 into that. Now when you have a look at it, you put 3000 into this, it gives you this number here, and you think, well, that's a bit weird, you know, it's a lot lower, it doesn't seem to fit the data at all. But remember that this is the z value you found. Now z doesn't mean anything. What you need is the price, and the price is y. So you're going to have to use the solve function. You say that ln of y equals the z value, which you found, solve it for y, and this is what the second regression model is predicting. But we need to take that extra step to actually turn it back into y, find the z, and then turn it back into y. And you can see it's higher than the 1.58, and that makes sense because if you remember the graph, the price was flattening off. So, you know, a better model would give me a higher price. The first linear regression is going to give me a price that's too low. The second regression is going to give me a price that's slightly higher, 1.70 in this case. So that's going to be the last part. And then you comment on it. So say basically that the third model gives you a better price, gives you a more realistic price, and it fits the data. You can even add it to your graph here, which would be quite nice. So that's about it. It's they're not very nice questions, but you know, just do it quite mechanically. There's if you go to the stats part of the Year 7 Cookdale Math site, then it will tell you yeah, it gives you another annotated question with which is similar, and you can go through all the steps there. Anyway, if it doesn't work, let me know.